This video focuses on analog to digital conversion. Basically, at its core is we want to take a voltage and give it a value. So, for example, if we have a signal that maybe moves from zero volt to 5 volt, at its core, all we want to know is we want to associate a number to that. And typically we have a limit on the lower voltage, that is, this is called the range. 0 to 5 volt is called the range. And usually we say, okay, let's assign a 0 value, and it depends on how many bits we assign. For example, PIC micro gives it 10 bits. Okay, when you have 10 bits, we know that when you have 10 bits, you will have 2 to the power of 10 possibilities. So what does that mean? That means I can basically have a value that is going to be represented by 0 hex. Let's use a decimal value. Let's not use hex. 0 decimal all the way to 1023 decimal. So if I have a 5 volt, I am theoretically able to convert any given voltage from 0 to 5 volt to a value corresponding to this. Okay, so for example, if we wanted to represent 2.5 volts, that would be roughly in the middle here, somewhere, depending on which side of this we do, somewhere in the 512 decimal value. Now, so that's basically an A to D conversion, an ability to take a range of voltages from 0 to 5 and give it a number. You might ask, so why are we doing this? Well, the reason we do that is because practically everything in nature that the computer needs to sense first has to be translated to voltage, whether it's a light, whether it's distance, whether it's the gravitational force of a star far in the distance, whether it's your DNA structure being analyzed, whatever is that we are analyzing, or a chemical property or whatever, we somehow have to translate that to a voltage, and then that voltage would be read into the computer by going through an A to D converter. And a lot of time this is just written as like this. Okay, even though we did a little bit of a pulse width modulation, that's the way going in the other direction, but actually we could take a number and turn it into a voltage as well. Of course, if it's called an analog to digital, when you go from 0 to 5 volt to a number, then digital to analog would be, to given a number, you can take it to a voltage. Okay, now I use 0 to 5 volt as a reference. It doesn't have to be 0 to 5. You can decide based on your system what is your lower range, what is your upper range, and you know how you want to divide that 10 bit or however many bits you have amongst the various possibility. In our case, in the PIC micro, they do have 10 bits available, so the possibilities are for 0 to 1024, and you can decide what your, they call this one V reference minus, and they call this one V reference positive, and you can decide whatever voltage you want it to be, the upper range and the lower range, and then the 1024 will be divided accordingly. Before I go away, there's another concept called resolution, and resolution is basically what is one count from 0 to 1 or 1 to 2? What is one count? The voltage equivalent to one count. So the voltage equal to one count in this would be basically 5 volt, which is the total volt range, 5 minus 0, or V reference plus minus V reference minus, divided by the total number that you have, which is 1024, and that will give you the resolution. Okay, which is roughly, for this system, the way I have drawn it, is 5 milliamp. Okay, roughly. All right, so, and we said that doesn't matter whether you are doing temperature, distance, light, color, chemical property, whatever. If you want a computer to read it, you have to translate it to a voltage, and then you have to be able to read that voltage in the form of a number, and then you can manipulate it. GPS, creating your location, and all of these things uses some form of A to D converter. Okay, now In this video, we're going to spend a fair amount of time focusing on one example, which comes with a PIC18F1220. Now, if you look at, there is a whole bunch of pins that are AN0, AN1, AN2, AN3, AN4. In reality, we only have one A to D conversion, but we are able to take this A to D conversion and tell it to get its input from one of these. Since when we are, for example, when you're sensing a temperature, you sense it, you don't have to sense it every second of time. You can sense it once and then come back and sense it a minute or 2 minutes later. And this allows you to take this thing and have, let's say, 10 different devices, in this case, 7 different devices, 0 through 6, and have one device come into channel 0, another one 2, 3, 4, 5, 6, and then you can move your A to D converter to read different one and give you a value. And since you have control over both sides, you know what you're reading. So that's a way of taking one A to D converter and be able to read 7 different things. Okay? Now, so you remember the ATCON1 we used to use to say all of these are digital? Well, if I want to use AN0 as an analog, I better make sure I don't set that ATCON1 to 7F, because we want one of them to be analog. If you want all of them to be analog, 0 through 6, then of course you have to say ATCON1 set to 0 instead of 7F. We'll come back. We'll come and talk about that in a little while as well. Okay, so we for the rest of this example, we're going to assume our input is being picked up and brought in on pin AN0, and then, as I mentioned before, we have 10 bits that represent the voltage across here. Now, we have lots of different ways we can configure our A to D converter. Let's start first by you taking a look at this. You remember we talked about what the range is. What's Vref minus and Vref positive for the thing? Well, depending on what value you put in here, you could say, hey, use the 5 volt and the ground that I'm powering my PIC18F1220 and use that to be the upper and the lower range. You can have one side be the external, you can have the other side be the external, or you can have both of them. There are 2 pins. You put whatever range of voltage you want on those 2 pins, and then you might ask, why would I want to do that? So sometime maybe the power supply is not precise enough, or maybe the range is too big, you want more precision. So you say, okay, reserve these 2 pins to give me the upper and the lower range of my A to D conversion. Great. Okay. The other one, remember we said that we have 6 different places where A to D conversion can be picked up at pin A0 through A6, and these 3 bits here, right here, defines which one they're coming from, channel 0, channels 2, all the way to 6. Now, gone and done are really an interesting pin. When I want an A to D conversion to take place, I'll go ahead and replace this, set this bit equal to 1, starts conversion. Now, you don't know when conversion is done until you keep looking at the same bit. When this same bit is 0, when you read it as a 0, then conversion is completed. Okay? Conversion complete, which means you can go read the value in the registers for the A to D converter, and there you have it. And then finally, this bit just turns off and on the A to D conversion. This is kind of unique. If you've never done it, you want to spend a little bit of time thinking about this. This bit, you set it to 1 to get the processor to start. Processor sets it to 0 to tell you they're done. That's kind of cool, I think, as far as that goes. ATCON1, we've been setting this to 7F all the way through the videos and labs and everything we've done so far, because we didn't want any of these pins to be analog. We wanted all of them to be digital. Now, for example, since we want pin AN0 to be analog, we have to make sure that this pin is set to 0. Otherwise, we won't have an analog. So that's one thing you got to do. Okay, let's see what else we got. Okay, the other register is at COM2. Now, what does that do? Oh, okay. So what this does, this allows us a whole bunch of things. And I'm not going to spend a lot of time on this. We can, most of the time, you're fine to leave them at 0 or the default value. This allows us to increase the conversion and the clock frequency that is fed to the A to D conversion. And I think the biggest way I can explain this is the slower you run it, the more accurate you're going to get the answer, because you're going to let things settle in. And for our cases, for here, unless you have a good reason to do it, we're going to keep everything kind of as fast as we possibly can, unless we figure out, hey, this is not working fast enough, accurate enough for us, and we want more accuracy. Okay. Now, the other pin that's kind of interesting is this whole business here. Now, if you recall, the A to D conversion, when it's completed, we're going to get 10 bits. Well, the SFR register and all of our registers are 7 bits. So how do we get 8-bit? The way we get it is actually the data is stored in 2 registers. One register is called A to D result low, and the other one is called A to T result high. So we have ADRESL and we have A to D RES high. Okay, we have a choice. We have a choice to put the 10 bits here plus these 2 bits. That is called, so conversion bit 0 goes in here, bit 7 goes here, bit 8 goes here, and bit 9 goes here. And this is called, this happens when we are making it right adjusted. So that's when the pin ADFM, this pin, is set to 1. Okay. Now, if you set the bit to 0, if you set this A to D format thing to 0, what's going to happen? A to D high is here and A to D low is here. But the way the data is going to be stacked, the data is going to be stacked by bit 2 here and bit 9 here, and then the 2 extra bits, bit 0 and bit 1 in here. So you say, why did they do that? What good is this? Well, one, they wanted to give us 10 bit, and you have to divide it to 8 and 2. That's the only way, because we got a byte and somehow we got to spread it across. And I think this is kind of nice. Sometimes you want accuracy. If I want high accuracy, but I have a smaller range, but I want to really see the higher accuracy, then maybe this is the right way to do it. Sometimes I don't care about accuracy. By the way, at any time you want the whole data, you can read both of them and figure out what the whole data is. But sometimes we want a shortcut. We don't want to have to read 2 bytes. If, for example, if I read this one, I'm basically giving up accuracy because I'm going to, don't see the 2 least significant bits, but I still kind of know where I am in the broader range of the spectrum. So if you don't want to read 2 bytes, the one will give you accuracy, the other one will give you a broader range. So it depends on what you want to do. You can use it either left adjusted, this one, or you can do right adjusted, this one. Now, having said this, these were all discussed as if you could have to do it manually, and that's the only way to do it. No, there are interrupts associated. There's an A to D interrupt, there's A to D flags, there's A to D, all of that stuff. So you can have A to D, once the conversion is complete, cause you an interrupt and pick up the interrupt and run with it. Okay, here is a quick outline of what you need to do in order to configure an A to D. You gotta select external pin that's going to be used. You got to configure the analog PIC. You got to set the voltage reference, whether you want it from the source, whether you want to provide your own as an external reference. Select the A to D acquisition time. 0 is good unless you have a good reason not to do it. A to D conversion clock, half the frequency is good unless you want to slow it even further down. And then you can turn on your A to D conversion. If you want interrupt, then you have to make sure there's other interrupts, the global interrupt and all that is set up. And then you also have cleared the A to D interrupt flag, enable the A to D interrupt, and set the priority to high or low, whatever it is you want to do. And then to start the conversion, you say go, set the go bit to 1, and you either manually wait for the done or you wait for the interrupt to happen, whichever way you prefer, or prefer whichever your program is needed to do that. And then you can go to add A to D result high and low to read it. Make sure that once you've read it, if you want an interrupt, to clear the A to D interrupt flag. Okay. All right. So for the next, oops, what did I do? So for the next conversion, you can go back up to the next conversion and start the process all over from step. Let's see, step 3 probably would be not even step 3. Just go ahead here and set the go done bit, and you can restart the process again. So that brings us to the end of the A to D conversion, and all this is doing is allowing you to take an analog signal between a V reference minus and a V reference plus, and given a specific number associated with it. In the case, we can have 16-bit, 24-bit, whatever bit, depending on the processor. But in the case of PIC Micro, we have 10-bit that's spread over 2 bytes, and that is corresponding to what voltage is being read at the time of conversion from the pin you have selected. And this brings us to the end of A to D converter overview.